Hello everyone, welcome back. So I'm starting a new series. So in this series, we are going to discuss concepts in physics and math that require special attention, meaning we will discuss those concepts in depth. So this will be aimed mainly towards rank booster and JEE advanced. All right, so when we start physics, one of the first thing that we learn is about the 7 base or fundamental quantities and the 2 supplementary quantities. Now, you will hear me often saying that these 7 base quantities, they are independent and complete. So in this video, I'm going to talk about what does it mean by independent, what does it mean by complete, and what are the implications. All right, so to keep the thing simple, we will consider only 3 of the base quantities: length, mass, and time. So this is an independent and complete set for studying rigid body motion. Now, once we understand the concept, we can easily extend this to include all 7 base quantities that cover all of physics. All right, so first, what does it mean by independent? Independent simply means one doesn't depend on other, meaning, for example, length doesn't depend on mass or time. Similarly for the others. Now, what does it mean by complete? Meaning, these base quantities can be used to describe all physical quantities for that specific problem, right? So in this case, for rigid body motion, length, mass, and time are everything that we need to completely describe rigid body motion. That means any physical quantity can be described using length, mass, and time. Now, for physical quantities, the function has a special form like so. Just as a simple example, speed. Speed is length over time. So length to the power 1, there is no mass, so mass to the power 0, and it's 1 over time, so time to the power minus 1. All right, so far so good. But how is this useful? Like independent and complete, how is that useful? Now, the rest of the video is about that. Now, this is the problem statement. Let's say given a reference set that is independent and complete, that is the reference set, we need to determine if a derived set is also independent and complete. And this is the example of a derived set. Okay, so a formal approach goes like this. So on the left hand side, I have the reference set, length, mass, and time. On the right hand side, I have the derived set, length over time, mass, and time. That is the example that I have taken here. Now, I'm assuming that this is equal to this. Now, how can I assume that? Remember, when a set is complete, that means any physical quantity can be described in terms of those base quantities where the function is defined like so, right? Now, here what I'm saying is, if this derived set to be complete, that means any physical quantity, I should be able to express it as this power something, this power something, and this power something. But I know that it is given to me that this reference set is complete. That means the same physical quantity I can describe as length to the power something, mass to the power something, and time to the power something. And when I equate this, somehow I should be able to find x, y, and g, right? So that is the logic behind why I am assuming this. Now, next is, how can I solve for x, y, and z? I have only one equations, but I have 3 variables here, right? That's where the independence come in. I know that the reference set is also independent, meaning, whatever the power of length on this side has to be the same, length has to be the same power on this side, right? So when I equate that, I get individual equations for a, b, and c, or x, y, and g, and then I try to solve that and see if that makes sense. Now, once I solve that, right, if I get a unique x, y, z for any abc, if I get a unique x, y, z, that means the derived set is also going to be complete and independent. Now, we will see that if we get a unique solution, that means that it is going to be independent. And if we get a unique solution for any abc, that will imply that it is also a complete set. All right. So this is abstract. Let's look at some concrete examples. I've just listed some concrete examples here. We will go through each of those in the next slides. But as you can see here, so this is my reference set, length, mass, and time. I have copied that here one more time. So this is trivial, right? Length, mass, and time is also independent and complete. That is actually given to us. But let's say take another set, length by time, mass, and time. We will see that this is also independent and complete. And depending on how we derive a set, it may or may not be independent, it may or may not be complete, right? We will see each of these examples in the next slide. Okay. All right, so this is the first case. This is a trivial case, and the given set is length, mass, and time, and the derived set is also length, mass, and time. Then of course if I equate this, remember this from the one of the previous slide. Now it just gives me x is equal to a, y is equal to b, and c is equal to g. That means for any so there is a unique xyz for any abc, right? So then this set is independent and complete. Of course this is a trivial case. This is a trivial case because these are the same, but this is just to this is just for warm up. Okay, let's go to the next example now. Okay, so this is the reference set and this is the derived set. So I write this equation here. Now if I equate the powers here, so length power a, here length power x, so a is equal to x, mass here is b, here is y, time is c here, and time here is in the denominator, so negative x, and time is on the numerator, positive g. So if I solve this, right, I get x is equal to a, of course it is straight away from here, y is equal to b straight away, then z is equal to c, x comes to this side, so c plus x, but x is equal to a, so g becomes a plus c. So as you can see, I get a unique value of x, y, z for any abc. Whatever the value of a, b, c you give me, right, I can find a unique value of x, y, and z. That means they are independent and complete. So the derived set is also independent and complete. Next example, this is my derived set here. So I write this equation. There is no t on the derived set, so I just write t power 0 here. Then when I equate the powers, I get a is equal to x, b is equal to y, and c is equal to 0. That's what I have written down here. Now, as you can see, there is a unique value of x and y for whatever a and b, right? So I get the unique values of the powers on the right hand side. That means that set is independent. However, the c is restricted. C cannot be anything. C has to be 0. Now let's think about this a little bit, right? So using this set, I cannot represent everything that this set can represent. Using this set, I can represent only the things this set can represent when t to the power is 0. That means this is not a complete set. It is not complete, right? So that is this example there. Next example, in this case, this is my derived set. So I have 4 quantities there. So I need 4 variables, x, y, z, and s. And I equate the powers like so. Once I do that, I get this. So notice here that only y is uniquely defined, right? But x, s, and z, there are 3 variables and I have 2 equations. What does that mean? I can choose one of x, s, and z arbitrarily, right? That means it is not independent, right? There are 3 variables, 2 equations here. There are 3 variables, x, s, and g, but I have only 2 equations, so I can choose one arbitrarily. That means it is not independent. All right, and there are no restrictions on a, b, and c. I can have a, b, and c whatever I want, so it is a complete set. So basically, if you can uniquely determine the right hand side powers, that means it will be independent, and if there are no restriction on a, b, and c, then it will be complete. But in this case, I'm not able to uniquely determine x, y, g, and s. In fact, I can arbitrarily choose one of x, s, and g. So that means it is not going to be independent. but there are no restrictions on A, B, and C, so it is going to be complete. Okay, next example. Here I have this as the derived set, the same process, and then I come up with this equation that results in this. And as you can see, I have a restriction on B. And another thing is here I have three variables, two equations. That means one I can choose arbitrarily. That means it is not independent. And then again, there is a restriction on B, so it is also not complete. Okay, this is the last example. Here, this is my derived set. I go through the same process and then I end up with this expression here. So there is now on the right hand side, my unknowns are x and y. And there is unique x and y for any AB. No matter what A and B you give me, there is unique value of x and y. So it is going to be independent. So that's fine. But C cannot be anything, right? C, C is, there is a restriction on C. That means it is not complete. All right. So it is purely linear algebra. As you can see, we are trying to solve and interpret linear equations. Now, based on that, I have some remarks here. So this is a little bit advanced. You will learn this maybe in your graduate studies, but this is also intuitive. So I thought I would put it in here. So let n be the number of elements in a set. So in my reference set, I have length, mass, and time. This is my reference set. So I have three elements. So nref is 3. Now the first is the derived set should have that many elements that is necessary, but it is not sufficient for the derived set also to be independent and complete. So the derived set must also have 3 elements that is necessary. It is not sufficient though. For example, this is my reference set, right? So this is the derived set. It has 1, 2, and 3, right? So this is also independent and complete, but it is not sufficient. Like in this case, I have also the derived set has 3 elements, but it is not independent or complete, right? So that is necessary. It is necessary, but it is not sufficient. All right. Second point is if the derived set has less element than the reference set, right? So my derived set has less element, that means it is not going to be able to completely describe all the physical quantities, right? So it is going to be always incomplete. So if it has less, then it will be always incomplete, right? So this is 2, this is also 2, so it is always going to be incomplete. Now if the derived set has more elements than the reference set, then some of them are going to be dependent, right? So they are not going to be independent. So for example, in this case, it has 4 elements, so it is not going to be independent, right? I thought I would just put it in here. You may be thinking, why is he making such a big deal about independent and complete? Well, this is why. So that we can change the base. For example, in physics, we typically use length, mass, and time as the base of fundamental quantities. But if I can find another set like this, which is also independent and complete, I can use this as the base or fundamental quantities instead of this. But why do we need to change the base? Well, there are several good reasons. You see, the concept of change of base is not limited only to describing physical quantities. It has a much wider applications. So I have collected examples from different applications so that we can appreciate the usefulness of this concept. All right, so first let's talk about convenience and explainability. In computer graphics, we use red, green, and blue as the base or fundamental colors to describe all other colors. But in art and design, they find it more convenient to use red, yellow, and blue instead. When describing the motion of a car on a road, we may find it more convenient to use the Cartesian coordinates, whereas describing the motion of planets or satellites, we may find it more convenient to use the polar coordinates. All right, now the next reason that I have listed is efficient information storage and processing. So I have a example here called principal component analysis. This is a bit of an advanced application. This is something that you will learn if you're going into machine learning, data science, signal processing, and such. But let me give you a very simplified explanation here. Let's say I have a bunch of data points. Now to store each point, I need two numbers, x and y coordinates, right? So this is my x, this is y. But if you look at this data, this lies mostly on a straight line here. So then I can say, instead of using x and y as my base or coordinate system, I can use this line and this line instead. Let me call this x prime and this is as y prime. Now, if I use this as the coordinate system, I need only one number, x prime, because the variation of this data on the y prime direction is very negligible, and I can neglect that. In many applications, actually, we can do that. So in the original coordinate system, I needed two numbers for each point. In the new change of base, x prime, y prime, I need only one number. So there is already a 50% saving. Sometimes in data science, each point will be a million dimensional data, meaning each point will require million number to store the data. But by doing this principal component analysis, you may come up with maybe 100 principal dimension. That means what you originally needed 100 million numbers to store, now you can store the same information with 100 numbers. So there is a huge saving in terms of storage, and it also makes it the data processing very, very efficient. Again, this is a little bit of an advanced example, but it's a very cool example. I just wanted to give a simplified explanation. So all these are teaser. The main reason actually we need to know is this, because this is a very frequently asked and easy to score question in NEET and JEE. That's why we need to know about this. At this point, I wanted to make one note before we proceed to solve problems from JEE and NEET. So the way I have been representing physical quantity, it is called dimensional representation. Essentially, dimensional representation allows to represent a physical quantity in a unique way, right? For example, let's consider sound speed. It can be this many meter per second, this many kilometer per hour, so on and so forth. So as you can see, the units are different, and based on that, the numerical values are different. But whenever we talk about speed, it represents length over time. That doesn't change whether we are talking speed in different units or speed of different things, right? It is always length over time. That means length to the power 1 and time to the power -1. So this is called the dimension. So the speed has dimension of 1 in length and -1 in time. So this is called the dimensional representation. In fact, any physical quantity can be represented as a product of a base physical quantity to the power something, and this something is called dimension. For the rest of the video, we'll talk about how is all this going to be useful for NEET and JEE. There are two different kinds of questions you can expect. The first kind is, given a set, can you use that as the base for fundamental quantities? For example, can you use velocity, linear momentum, and force as the fundamental quantities? So in this case, for any A, B, C, we will try to find if there are unique X, Y, and G. The second type of question will be change of base, and this is more frequently asked. In this case, for example, given energy, can you express that in terms of velocity, momentum, and force? So in this case, physical quantity is given, so we'll try to solve for X, Y, and G. I have a few examples for each of this. We will see that next. The first example is from Verma. Which of the following sets cannot enter into the list of fundamental quantities in any system of units? And we are given some choices. Here actually it is indirectly asking if these quantities are independent or not. Remember, for a set to be used as a base or fundamental quantities, it has to be independent and complete. In this case, we are not so much worried about completeness because there may be other quantities in the list which will make it complete. So we are only worried about the independent in this case. So we will follow the normal procedure. Length, the reference set is length, mass, and time, and the derived set is length, mass, and velocity. Length, mass, and velocity is length over time. So what we do is this to the power A, this to the power B, and this to the power C. So this to the power X, Y, and G, and we try to see if we can find a unique X, Y, Z for any A, B, and C. And we can, of course, we can just do like we did earlier, but there is actually a simpler approach in this case. If you look at this, right, length, time and velocity. Length, time and velocity is length over time. We can, just by looking at it, we can see that these three are dependent. For example, velocity is length over time, right? So we can already see that this is dependent, and you can also try to do it the formal way. I think in one of the previous examples we have that length, time and velocity. So we have done it already the formal way. You can just check it out, but just by looking at it, you can see that they are dependent. So this cannot be used, this cannot enter into a list of fundamental quantities. Then B is the correct choice. Next example, velocity, linear momentum and force can be used as base quantities, true or false. Okay, velocity is length over time, linear momentum is mass times velocity, that is mass times length over time, and then force is mass times acceleration, so mass, acceleration is length over t square. So we follow the process that we did earlier. So that here the reference set is length, mass and time to the power a, b and c, and the derived set is velocity, linear momentum and force to the power x, y and z. So velocity is length over time to the power x, linear momentum is mass, length over time to the power y, and force is mass, length over t square to the power z. We will try to equate the powers now. So a is going to be length to the power x plus y plus g. So that is this one. I'll try to equate the power of mass now. That is b equal to, there is no mass here, there is y plus z. Alright, and then c. Now I'll try to equate the power of, this is done. Now the time. C is going to be, this is minus x, here minus y, here minus 2z, right? So we have three equations, and let's try to solve for it. Now, just by looking at it straight, right, from this y plus g is b, so this is b. So this actually straight away gives me, x is equal to a, and b goes to the other side, that is a minus b. So this is the value of x. Next, I see that, so this one I can write it as minus x minus y minus z and then minus z. Basically I split this. So x, y, z, so this is minus x minus y minus z is going to be minus a. So this is going to be minus a. So this gives me z comes to this side, z is going to be minus a minus c, minus c. So this is z, and then what is remaining is y is b minus z, y is equal to b minus z, right? Y is equal to b minus g. Okay, b and z is minus a minus c, so minus plus a plus c, right? So basically y is equal to a plus b plus c. All right, here as you can see, if you give me any a, b, c, right, I can find a unique x, y and g. That means the derived set, velocity, momentum and force, it is independent and complete. So yes, it can be used as the base quantities. So this is true. Next example, if mass, velocity and time are considered as fundamental physical quantity, then dimensional formula of force will be, so this is a change of base type problem. I'll show you two different methods. Normal method, this is how you will see it in the book or online videos. I'll also show you a direct method. Let's do it this way first. So I want to express force in terms of mass, velocity and time. Mass, velocity and time. The way to do that is I assume force is equal to mass to the power x, velocity to the power y and to the power z. and both sides I'll try to represent in terms of the common base, that is mass, length, and time. And from there I can solve for x, y, and z. So force is going to be mass, and acceleration is length, and time to the power minus 2. So on the right hand side, mass to the power x, velocity is length over time to the power y, and then time to the power z. I equate the powers now. Here mass to the power 1 and length to the power 1. So this one is going to be on this side x, length this side 1, on this side y, time this side minus 2, on this side minus y plus z. But I know y is 1. So this tells me z is equal to minus 1. Z is equal to minus 1. So that means mass to the power 1, velocity to the power 1, and time to the power negative 1. Then A is the correct choice. All right. So let me show you another approach. So this is called direct approach because I will try to do it without writing down these linear equations. And the way to do that is, let's write down the formula for force. Force is equal to mass, some mass quantity, and some acceleration is some length quantity over time square. Right now, once I do that, I try to regroup these quantities so that I get to the destination. My destination is I want in terms of mass, velocity, and time. Sometimes I may have to multiply and divide by some other quantities, but in this case, if you just stare at it, I already have mass, and then I try to group length with one of time. So this gives me velocity, length over time, and then time is still there. So this is going to be mass, and then velocity, time to the power minus 1. I directly get this same answer. Okay, so this approach, you are sure to get the answer because when you write down linear equations, you can easily solve it. But as you can see, this process can be a little bit slow. This side is a little bit risky because it depends on how you group, and sometimes you may feel like you are stuck. But with practice, you can you can definitely do it. And if you can do it right, this side is very, very quick. You don't have to write down the equations and solve it. All right. So one question you may have in your mind is, what is the guarantee that you will get the same answer as this side? Right? It is actually guaranteed because if this is given as the fundamental quantities, that means by definition these are independent, right? That means x, y, and z will have a unique solution for a given given physical quantity, right? That means whether you do it this way or this way, you will arrive at the same answer. Okay, we'll see some more examples next. Next example, express energy in terms of velocity, linear momentum, and force. All right, velocity is distance over time. Linear momentum is mass times velocity, mass, distance over time, and then force is mass times acceleration. Acceleration is distance over time square. So let's try the direct way first. Energy can be same as work, which is force times distance. All right, so force is already a fundamental quantity. Then how do I represent distance in terms of velocity, momentum, and force? All right, so that seems a little bit tricky. Let me expand F instead. F is mass times acceleration distance over time square, and then there is another distance. Now if I look at it, mass, distance, and time, mass, distance, and time, so this is P, and distance over time, so this can be velocity, right? So this is P V, and there is no force involved, so F to the power 0. Then D is the correct choice. All right, we can also try it in the normal approach and see if we get the same answer. So let me express energy in terms of mass, length, and time. So that is going to be mass length square and t to the power minus 2, and we want to express this in terms of velocity. Velocity is going to be distance over time to the power x, and then linear momentum is mass distance over time to the power y, and then force is mass distance over time square to the power z. Okay, now I equate the powers. Mass to the power 1 here, so this 1 is going to be there is no mass here, this is y plus g. Okay, and then length to the power 2, so 2 is going to be equal to here x plus y plus z. All right, and then minus 2 is going to be this one, this is minus x, this is minus y, and this is minus 2z. All right, now if you stare at these equations, let's take these two first. Y plus z, so this is equal to 1 from here, so this is 1, so then x is going to be 1, right? Okay, now here this one I can write this as, you know, minus x plus y plus z minus z. I just rearrange this here, but x plus y plus z, I know that to be 2, so this is 2, so this is negative 2, negative 2 cancels out, so this gives me z is equal to 0, right? See, this negative 2 and negative 2 cancels out, so if z is 0 and y is going to be 1 from here, right? So take this and take this together, this gives me y is equal to 1. So what do I get? X is equal to 1, so that is velocity to the power 1, momentum 1, v to the power 1, p to the power 1, and z, that is force 0. That's exactly what I get, right? It's the same answer. Next example, if velocity of light c, universal gravitational constant g, and Planck's constant h are chosen as fundamental quantities, the dimension of mass in this new system is. All right, so let me write down the formulas first. C is distance over time, and then g comes from, you know, the force of gravitation, g m by d square. So this gives me g is equal to f d square, and this is m square basically. Okay, h comes from the equation E is equal to h nu is the frequency, so this gives me h, and energy is same as work, that is force times distance, and new frequency is 1 over time, so the time goes up, so this will be f dt. All right, now let's try the direct approach first. Okay, I want mass. If I start with mass, I have to multiply with something and divide by something, so that's going to be a little bit tricky. So but if you look at this equation, right, so there is m square here, so somehow if I divide this like g and h, right, some things are going to cancel out, and I'm going to end up with m square, and then I can take the square root. All right, so that's what I'm going to do. So I will do h over g, so that m square is comes to the top, so h is equal to f d t divided by g is f d square over m square, so m square is going to come to the top, force cancels out, 1 d cancels out, m square here, so t over d, when this comes to this side, it will be d over t, which is c. All right, so this m square then is going to be h over g, and then c, right? D over t is c. Okay, so this gives me m is equal to h to the power half, I'm taking square root both sides, g to the power negative half, and c to the power half, right? H to the power half, c to the power half, g to the power negative half, then a is the correct choice. You can also try the normal approach and write down the linear equations and make sure that you get the same answer. Next example, if force, velocity, and time are considered as fundamental physical quantity, then dimensional formula of density will be, all right, density is mass over volume, that is dq. Okay, somehow I want to represent this in terms of force, velocity, and time. I know that mass appears in force, but let me try to bring in force here. So mass times acceleration is force. Acceleration is d over t square. Then I'm going to also multiply the reverse. So t square d. So basically this whole thing is just 1, right? Then what I can do is I can group this. So this is force. Then I want velocity and time. I have d to the power 4. 3 plus 1 is 4. So if I multiply by t square and then again divide by t square, right? So this is going to be v to the power minus 4, like v is equal to d over t, right? And this is the inverse of that, d4 and t4. And this is nothing but t to the power minus 2, right? So what do we have? F v minus 4 t minus 2. The B is the correct choice. Next, I have 3 example problems that you can try yourself. Definitely try the direct method first, and just for practice also do it the normal method and make sure that you get the same answer. The correct answer, I will put it in the video description. Or should I do it? Okay, but make sure to pause the video first, try it yourself and before looking at the answer. So let's do it. If force, length, and time are taken as fundamental quantities, then what will be the dimension of density? So density is mass over volume. So mass appears in force. So mass times acceleration is force. So I want d over t square. So this makes acceleration. Then I'll multiply also t square by d so that this thing is 1. Then what I want to do is I group like this. So this is my force, right? And then I have length. So this is going to be L4 and this is t square, right? So F, so this when it goes to the numerator, minus 4 and then T2. So F L minus 4 T2 is the correct choice here. All right. This one, if force, acceleration, and time are taken as the fundamental physical quantities, find the dimension of energy. So energy is force times distance, same as work. So force is already there, and I want acceleration and time. So to make acceleration, distance over time square, I multiply by time square. So this is basically a, and this is t square. So f a t square. C is the correct choice here. And this one, force, velocity, and time are taken as the fundamental quantities. Then dimension of mass. All right. So mass is going to be, mass appears in force. Force is, what I want to do is multiply by acceleration and then again t square over d so that this whole thing is 1. So this is force, and then velocity I want, so I will take one of this, right, one time. So this remains as t, and this is uh, t over d. T over d is basically velocity to the power minus 1. So f v minus 1 t, f v minus 1 t, d is the correct choice. All right, so this is the last slide. So let me just give a recap. We started talking about the base quantities, and then I said they are independent and complete, and then we spent a lot of time discussing what does it mean by independent and complete, and we saw several examples of that. Then we talked about change of base. I gave a few examples from different fields. Then we discussed how is that concept useful for NEET and JEE, and we basically we saw that you can be asked two different kind of questions, and one of that is change of base, which happens to be one of the frequently asked questions. And then we saw several examples of that, right? All right, so there is two key takeaway from this whole video. One is, if you see this kind of problem, definitely try the direct method, practice that, because as you can see with that, many times you can just solve it with one line, right? So it's really fast. And then second is, be smart about solving linear equations, meaning, if you happen to solve this kind of problems using the normal approach where you will end up with some linear equations, or also some other problems in physics, oftentimes you will end up with a set of linear equations. If you do end up with that, be smart about solving those equations. Oftentimes I see, when students want to add two equations, they write it down again, put a plus sign, and do it like that. Don't do it like that. I typically just put two lines, meaning that I'm using these two equations, and do some math in mind and write down the final result. This way you can do it really, really quick, and you can definitely practice this. With practice, you'll get better. Okay, one last thing is, in NEET and JEE, many people appear for the test, right? So this happens to be one of the easier kind of problems, so many people will know. But what will differentiate you is be able to do it really fast. And some techniques like this can really help. So I think I'll end this video here. Thank you very much. I'll see you in the next video.